In the previous lecture, we saw one technique through which the bandwidth of a quarter wave transformer or a QWT can be improved. And that was involving a means by which we are essentially adding more number of QWTs between the main line and the resistive load that is to be matched. And we also said that in that technique, by keeping the individual or the partial reflection coefficient at every junction of two lines or the last line and the load, by keeping all those reflection coefficients the same as one another, we could achieve multiple minimas in the frequency response of gamma in close intervals. So what we saw effectively was we had given a name for that kind of an impedance transformer, and that is called as equal gamma transformer. And we had multiple sections. Because the number of sections can be anything, or the number of matching transformers, or the number of transmission lines in the overall matching transformer. So, if this is the source and this is the main line, that is Z0, then there can be many number of intermediate sections. Let's call it Z1, Z2, all the way till the last line, that is Zn, which is terminated with some load ZL, which obviously is real, because the whole idea or the whole notion of the QWT is based on matching real loads. And the electrical length of each section is equal. We assumed initially it was some theta, but we know that the physical lengths must be lambda by 4. So we had defined that the reflection coefficient, the partial reflection coefficient at the junction of Z0 and Z1, that is over here, we called it as gamma 0. Here we called it as gamma 1. Here we called it as gamma 2, and so on. And the last one we called it as gamma L. So what we saw over there was that we applied the theory of small reflections to find out what would be an approximation for this overall reflection coefficient gamma that is offered by this entire impedance transformer. So if I were to label this, it is between these 2 points, the main line and the load. So this is what is the main line. So what we had effectively seen in case of the equal gamma transformer was that we could represent gamma as an algebraic sum of each of the individual reflection coefficient accounted for by their individual phase. So this is gamma 0 plus gamma 1 times e raised to minus j2 theta plus gamma 2 e raised to minus j4 theta, and so on until we have gamma L, which is corresponding to the nth section. So therefore this is e raised to minus j2n theta. So we can say that essentially gamma L and gamma n are identically the same. So then we had said that a solution can be obtained for the minima in gamma when all of these coefficients are made equal. So we had seen some cases if all of these gammas are equal, then let us say we had taken different values of n, this capital N, and we had seen that accordingly when you plot the mod gamma as a function of theta, the number of minimas change accordingly. So for n equal to 1, we saw something like this. So this was pi by 2. So for n equal to 2, something like this we saw. There are essentially 2 minimas because n is now 2, and we had found some values for these minima also. So if I am not wrong, they were 0.375 pi, 325 pi and 0.675 pi. So something like that. And we also saw for n equal to 3, this is for n equal to 3, there are 3 minimas. One minima is at pi by 2, the first is at pi by 4, and the third is at 3 pi by 4. So now this is what we had proved and seen in the previous lecture, and this is what is called as the equal gamma transformer. What we are seeing is that as the number of sections, the number of intermediate matching sections in the transformer is increased, so do the number of minimas in the frequency response for gamma also increases. Thereby, the bandwidth or the range of frequencies over which the gamma is kept below a certain value, that also increases. So therefore, this is the property of the equal gamma transformer. And we discussed very briefly that this is very similar to what people call as a Chebyshev type of response. Now, let us look more closely at this response. The very underlying definition of the performance or the frequency response of the mod gamma for an equal gamma transformer is the concept of closely spaced minima. Closely spaced minima. So there are distinct number of minima, but they are close to each other. So this leads to there being some kind of a local maxima between two successive minima. So therefore, this kind of local maxima in the middle, this kind of behavior are called as ripples. So there may be certain applications where these ripples may not be needed. Suppose there is an application where somebody might ask, can we do away with these ripples? Rather, can we have a kind of a flat response as long as the gamma is low? As long as the gamma is low, can we have a flat kind of a response? Close to 0. Well, that's possible. And those kind of impedance transformers which try to give you a flat response for that range of theta or that range of frequencies where the gamma is supposed to be low, those kind of impedance transformers are called as maximally flat transformers. Maximally flat transformers. Now this name maximally flat you may have heard of in your signal processing courses, in particular in the digital signal processing related courses, where a very popular technique exists for a filter that is also based on a maximally flat kind of response, and that is called as a Butterworth filter. So therefore this kind of transformer is also called as a Butterworth transformer. So the Butterworth transformer is based on a very simple concept. The difference between a maximally flat or the Butterworth transformer versus the equal gamma transformer which we have been seeing so far, the equal gamma transformer has different distinct roots placed in close proximity, or different distinct minimas kept in close proximity over theta. But the characteristic of the maximally flat transformer is it is based on repeating of minimas. Repeated minimas. So what that means is you have multiple minimas but at the same point, or multiple roots but at the same point, or that at the same value of theta. So in that case, Butterworth gave a very nice expression where he said, let us try to define gamma as a function of theta. Obviously gamma is a function of theta. If you notice in the previous page, even here the gamma is indeed a function of theta because of the phases. So he said, let us define the gamma of theta in such a way that we will have multiple roots at the same point. And the easiest way to do that is to have a binomial. Where k is some constant, n, capital N, indicates the same thing as it was indicating so far. That is the number of sections of the matching transformer, or the number of transmission lines in the matching transformer, and theta is the electrical length of each of those. So now what you see, the property of this binomial power is that there are multiple roots of this equation at a single point. So the question is, when would this binomial have a root? This would have a root when theta becomes pi by 2. So the minimas or the roots will be there at pi by 2. So if the value of capital N is 1, there will be one root. If the value of N is 2, there will be two roots. So this uses the concept of repeated roots. So using this, Butterworth claimed that the response in mod gamma as a function of theta will be the flattest possible response that can be achieved around the minima point. Now, another something that's very important to know, another piece of information that is very important to know is that if you take the first n minus 1 derivatives of these, they can all be set to 0. So that further brings us back, or that further repeats the concept of that repeated root or the repeated minima thing that we want. So now what we are essentially looking for is this binomial, that is raised to the power of n, it can be expanded. At the same time, let us not forget what the theory of small reflections tells us. The theory of small reflections tells us that in general, whatever be the nature of the matching transformer, whether the gammas are equal or not equal, that's a different thing. But the expression for gamma, the overall gamma as a function of the individual reflection coefficients, does not change. In case of the equal gamma transformer, we had ourselves set all of these coefficients as equal. But in case of the Butterworth transformer, that will not be the case. But this equation is still valid. So effectively, we need to find out now what will be the individual gammas or what will be the individual impedances of the line. That is the question. So now let us try to answer that question. So let us say I'll take the mod of this gamma theta. That's like saying it's mod of k times mod of this quantity 1 plus e raised to minus j2 theta raised to n. So one thing that I can do is I can take e raised to minus j theta common and say that this becomes mod k times e raised to minus j theta mod times, I can take this outside this bracket, and so in the bracket there will be e raised to plus j theta, because this product will then become 1 plus e raised to minus j theta, the whole raised to n, even this will be raised to n. So the mod of e raised to minus j theta is always 1, so therefore this vanishes. So what we will get is mod k times e raised to j theta plus e raised to minus j theta, the whole raised to n. So using Euler's identities, this is nothing but representative of twice of cos theta. So therefore what we will get is essentially 2 raised to n times mod k times mod of cos of theta raised to n. Right? This is what we can represent this expression for gamma as. So now the way to solve for this k can be found by applying the DC condition. So let us say we have this kind of a impedance transformer. We have this kind of an impedance transformer which can have any n number of sections. But this source, essentially, we make the frequency of it as 0. So then in that case, if the frequency becomes 0, theta will become 0. So then in that case, we can do away with this term. But then, in that case, what is the other meaning of it? This also means that if we make theta as 0, either the frequency is 0, which is one way to look at it, or the other way to look at it is if we are making theta as 0, the lengths of each of these individual sections would essentially be nullified. So it is almost like saying this load is directly connected to the main line. There is no matching section. So that means it's like saying that the main line is directly connected to the load. So therefore, what will now happen is if theta becomes 0, that is gamma of 0, mod gamma of 0 is nothing but 2 raised to n. So cos theta will become 1. So 2 raised to n times mod of k. So in this case, what will happen is that the main line Z0 will be connected to the load. So therefore, gamma of 0 is nothing but this ZL minus Z0 divided by ZL plus Z0. Right? So in that case, we can actually remove the mod sign, and because 2 raised to n will always be positive, so whatever is the sign of gamma of 0, that will be the sign of k. So that means gamma of 0, that is nothing but this quantity ZL minus Z0 divided by ZL plus Z0. This will be equal to 2 raised to n times k. So therefore, it is only too easy to say that k will be 2 raised to minus n times ZL minus Z0 divided by ZL plus Z0. So this is what is the value of k. Now, let us go back to the starting equation for the binomial or the Butterworth transformer. So we had said that gamma of theta is written in this format: k times 1 plus e raised to minus j 2 theta the whole raised to n. So we can very easily expand this bracket using the binomial theorem, which all of you must be familiar from your high school education. So this essentially will be something like this: k times 1 plus e raised to minus j 2 theta plus n combination 1 e raised to, it will be n combination 2. This will be n combination 1, n combination 2, and like that. So times e raised to minus j 4 theta all the way till ncn e raised to minus j 2n theta. So therefore, what we can say is this is the net gamma that is offered by the impedance matching transformer. That is this gamma, which is also a function of theta. So now what we have to do is we have to essentially make this equation valid in this case also. So as I said earlier, that the values of the individual gammas can change. However, the theory of small reflections will still be valid. So therefore, let us now equate this from the theory of small reflections to these. So as I said earlier, gamma n and gamma L are the same. So this is what it is. So now what we can say is we can equate each of these complex exponentials with their coefficients. So therefore, what is now going to happen is something like this. Gamma 0 will be equal to k. Gamma 1 is equal to k times nc1. So for sake of completeness, we can write k times nc0. Gamma 2 will be k times nc2 and so on. So therefore, for n varying in the range, or small n varying in the range from 0 to capital N, I can say that every individual reflection coefficient, small n, will be equal to k times nc small n. That's all there is. Now, let us not forget how these individual reflection coefficients are defined. We have already defined these individual reflection coefficients when we were discussing the equal gamma transformer as well. So that is nothing but z of n plus 1 minus z of n divided by z of n plus 1 plus z of n. Now since gamma n is same as gamma L, we will say gamma of capital N is nothing but ZL minus Zn divided by ZL plus Z capital N. So these are important. So now we can rewrite this gamma definition in a little different way, or yeah, it's not necessarily needed. You need not effectively write the gamma in a different way. So effectively, what can we say? So we said that gamma n is equal to k times nc small n. So gamma n is defined as Zn plus 1 minus Zn divided by Zn plus 1 plus Zn, and that is equal to Ncn times, now we'll put the value of k that we know already from our discussion, that is 2 raised to small n, sorry, minus capital N times Zl minus Z0 divided by Zl plus Z0. So if you know the load impedance and the mainline impedance, and you know which kind of transformer to design, that is using the number capital N, then you can very easily start from the Z0 side and move step by step to the ZL side, and using this equation you can calculate each of the impedances right from Z1 to Zn. That's it. So if n is equal to 0, that means it is Z0, that is the main line. And n equal to capital N means Zn, that is the last line before the load. And if n equals n plus 1, that means it is ZL, the load impedance. So that's all there is. That's all there is. So then let us take an example. Let us take a very brief example of how to work with the Butterworth or the binomial transformer. Let us take the same example which we had taken when we were discussing the approach with multiple minima or the equal gamma transformer. So there we had said there is a main line of impedance 50 ohms and that is to be matched to a load of impedance 100 ohms. So if I now were to solve using binomial transformer, let us say I take the very simple case, that is n equals 1. N equals 1. So then let us say what I will need is something like this. This is the line and the transformer I will need. So therefore let us use the impedance calculation equation which we needed. So there is just one impedance which we need to calculate. So therefore Z1 minus Z0 divided by, so all we need to find out now is the gamma 0. And that is equal to NC0 times 2 raised to minus n times ZL minus Z0 divided by ZL plus Z0. So if n is 1, we will get 1C0. So 1C0 is 1 times 2 raised to minus 1 times ZL minus Z0 divided by ZL plus Z0. That is 100 minus 50 divided by 100 plus 50. So that will be 50 divided by 150 or 1 by 3. And here the only unknown is Z1. So Z1 minus 50 divided by Z1 plus 50. That is equal to 2 raised to minus 1 times this. So what we get is effectively this becomes 1 by 6 and so you can find out what is Z1 from this. So what will that be? So 6Z1 minus 300 would be equal to Z1 plus 50. So 5Z1 would be equal to 350. So that means Z1 is 70 ohms, which interestingly is very close to that 70.71 which we normally have with a quarter wave transformer, because if the value of n reduces to 1, whether you are using the equal gamma transformer or a binomial transformer, the solution will be very, very similar. So that is how you can solve for it. So then in that case, you have gamma 0 and you have gamma of L. So in this case, what we will have is gamma 0 will be 70 minus 50 divided by 70 plus 50. That will be 1 by 6, and gamma 1, or sorry, gamma L, that is 100 minus 70 divided by 100 plus 70. So that will be 3 by 70. So therefore, using theory of small reflections, I can say that gamma is equal to gamma 0, that is 1 by 6, plus gamma L, that is 3 by 70 times e raised to minus j 2 theta. This is the case for when n is equal to 1. So let's take another example. I mean, for the same specifications, let us take the case for when n is equal to 2. When n is equal to 2. So then in that case, what we will have? Z0, Z1, Z2, and finally the load, that is ZL. So we can mark the reflection coefficients here, gamma 0, gamma 1, and gamma L. In that case, let's go back to our impedance calculation equation. So let's first calculate Z1. That will be Z1 minus Z0. This is for gamma 0. That will be divided by Z1 plus Z0, which will be equal to 2C0 times 2 raised to minus 2 times ZL minus Z0 divided by ZL plus Z0, which is 1 by 3. That will not change. So this will become 1. This will become 1 by 4. So this will be 1 by 12. And if you substitute Z0 as 50, you will get Z1. So Z0 is anyway 50, we know that. I've already calculated Z1 for you. That comes out to be roughly around this value, 59.07 ohms. The next step is to calculate Z2. So for that, we are going to use gamma 1. So gamma 1 is Z2 minus Z1. So now you can substitute this 59.07 divided by Z2 plus 59.07. That will be 2C1 times 2 raised to minus 2 times 1 by 3. So 2C1 is 2 and this is 1 by 4. So this will be 1 by 6. Again, the calculation will be slightly tedious. So already I have calculated Z2 for you using this equation, and that roughly comes out to be 82.44 ohms. Now let's take one last case where n is equal to 3. So for n equal to 3, I will not draw the diagram this time. We will have Z0 followed by Z1 followed by Z2 followed by Z3 and then ZL. So again here we will have gamma 0, gamma 1, gamma 2 and finally gamma L. So then again let's start by calculating gamma 0, which is Z1 minus 50 divided by Z1 plus 50, and that is equal to now n becomes 3, so 3C0 times 2 raised to minus 3 times 1 by 3. So from here you can get the value of Z1. When I calculated it, it came out to be somewhere around 54.34 ohms. And gamma 1 is Z2 minus this 54.34 divided by Z2 plus 54.34, that is equal to 3C1 2 raised to minus 3 times 1 by 3, and here Z2 comes out to be 69.78, again very close to 70, and finally gamma 2, where we use Z3 minus this value 69.78 divided by Z3 plus 69.78, that is 3C2 times 2 raised to minus 3 times 1 by 3, and over here Z3 comes out to be around 89.59 ohms. So now if we want to plot the gamma, so you can actually calculate each of these two impedances. So you can calculate gamma 0, gamma 1 and gamma L, in this case for 2 also, that is ZL minus 82.44 divided by ZL plus 82.44. So then in that case the net gamma will be something like this: gamma 0 plus gamma 1 e raised to minus j2 theta plus gamma L e raised to minus j4 theta. Now the values of gamma 0, gamma 1 and gamma L will not be the same. So whatever it is, you can find out for yourself. Likewise, over here we will have the net gamma as gamma 0 plus gamma 1 e raised to minus j2 theta plus gamma 2 e raised to minus j4 theta plus gamma L e raised to minus j6 theta. And you can now plot the mod gamma in each case as a function of theta, and you will see something like this. You can make use of any numerical tool like MATLAB to do this. So what essentially you will see is something like this: mod gamma as a function of theta. This is obviously when n is 1. For n is 2, you will see something like this. This is for n equals to 2. And for n equal to 3, you will see an even more flatter response, which is something like this. So therefore, this will be pi by 2 as always. This is what the binomial or the Butterworth transformer looks like. It is also called as a maximally flat transformer. So therefore, just by changing the individual reflection coefficients, we are able to observe a very significant difference in the frequency response of the impedance transformer, that is mod of gamma versus theta. So there may be some applications where you may need maximally flat responses. There may be applications where ripples are okay. In that case, you have a choice. You can either use the Butterworth transformer as needed, or you can use the equal gamma transformer as needed. So this sort of tells us that indeed there are ways in which we can obtain the improved bandwidth for matching any load to a transmission line using quarter wave transformers. And there is not just one way. We saw two ways. effectively in this course so far. Obviously, the common drawback between the equal gamma transformer and the Butterworth transformer is that you will have to sacrifice more space if you want more bandwidth. So therefore, you have to add more number of transmission line sections in the matching transformer as you want more and more bandwidth, because as n increases, so does the bandwidth. So with this, we come to the end of the discussion on how to match real loads and whether we can improve their bandwidth. Obviously, there are other ways also in which we can match real loads, but that we shall be discussing as part of the broader case where we can actually use those techniques not just for real loads but for complex loads as well. So more on that topic in the next lecture. Thank you.